Welcome to the lecture for section 8.3 in Calculus 2. We're looking at integration techniques specifically with trigonometric integrals. At the moment, our inventory of integrals involving trigonometric functions is really limited. For example, we can integrate the basic trig functions found in Table 8.1, but have not yet encountered integrals such as higher powers of trig functions, for example, the cosine of to the raised to the fifth power of x dx, or even the product of trig functions with powers, for example, the integral of cosine squared x times sine to the fourth power of x dx. The goal of this section is to develop techniques for evaluating integrals involving powers of trigonometric functions. These techniques are indispensable when we encounter trigonometric substitutions in the next section. So first we're going to look at integrating powers of sine or cosine. Two strategies are used when evaluating the integrals of the form integral of sine to the power of mx dx or integrating cosine to the power of nx dx, where m and n are positive integers. Both strategies use trigonometric identities to recast the integrand as shown in the example below. Example 1, evaluate part A, the integral of cosine raised to the power of 5x dx, and B, the integral of sine raised to the power of 4x dx. For part A, integrals involving odd powers of cosine x or sine x are most easily evaluated by splitting off a single factor of cosine x or sine x, whichever function you're using. In this case, we would rewrite cosine to the fifth power of x as being equal to cosine to the fourth power of x times cosine x. Notice then what we can do is cosine to the power of 4 of x can be rewritten in terms of sine x using the identity cosine squared x equals 1 minus sine squared x. The result is an integrand that readily yields to the substitution of u equals sine x. So let's see how that works. So the first thing that we're going to do is rewrite cosine 5x as cosine 4x times cosine of x. And when I say cosine 4, I'm talking about cosine raised to the power of 4. Okay? Well, since cosine squared equals 1 minus sine squared, then cosine to the power of 4 is 1 minus sine squared squared, right? Cosine squared squared would be cosine to the power of 4. So we substitute in that Pythagorean identity, all right? If we then let u equal sine x, then du would be equal to cosine x. So notice what we get is simply 1 minus u squared du, because du is equal to cosine x dx. So that takes the substitution of all the outside pieces. This is a really easy integral to solve now. We simply square that by foiling it out, and we get the integral of 1 minus the integral of 2u squared plus the integral of u to the fourth. These are very easy integrals, power integrals to solve. We solve them all and then substitute back in u equals sine x, and we get our final answer, which is sine x minus 2/3 sine cubed of x plus 1/5 sine to the fifth power of x plus c, the constant of integration. So this makes, by helping us rewrite these and then doing some simple trigonometric identity substitutions, these become much easier substitution problems to solve. Now let's look at part B. The integral of sine raised to the power of 4x dx. With even powers of sine x or cosine x, we use the half angle identities from trigonometry to reduce the powers in the integrand. Remember that from trigonometry, sine squared of x equals 1 minus cosine of 2x. This is not a power now. We've changed the argument. And that's what we're trying to do, is we're trying to get rid of the powers inside of the integrand, inside of the integral so that we don't have a chain rule problem, okay? So the sine squared of x is equal to 1 minus cosine of 2x. This is a double angle or half angle identity all over 2. Cosine squared equals 1 plus cosine 2x over 2. Now these are easy to get confused. And there's a great mnemonic that helps us remember this, and that is sine is minus. Sine is minus. So that the half angle identity for sine is minus. 1 minus cosine 2x, whereas the cosine squared identity is 1 plus. So this is a great way to remember that identity. Sine is minus, or to remember them both actually. So since sine squared equals 1 minus cosine of 2x over 2, and we have sine to the fourth, notice this is 1 minus cosine of 2x over 2 raised to the power of 2, because sine squared squared is sine to the fourth. Okay? If we simply square this out now, FOIL this out, we get 1/4 minus 2 cosine 2x plus cosine squared 2x. All right. Now we're going to use the half angle identity again for cosine squared 2x. So we're going to substitute that in here, okay? So we're doing it each time. All right. Once we do that, notice that we get, and simplify it, we get 1/4 times the integral of 3/2. Now where did the 3/2 come from? Okay. Well, we make this into two fractions. So 1 plus cosine of 4x over 2 gives us 1 over 2 plus 1/2 plus 1/2 cosine 4x. So that 1/2 plus 1 gives us the 3/2 minus the cosine 2x is still there, plus 1/2 times the cosine of 4x. Now we can simply take the integral of all of these and integrate them, and we get our final answer, which is 3x over 8 minus 1/4 times the sine of 2x plus 1 over 32 times the sine of 4x plus c, the constant of integration. Okay, so these are helping, these identities help us get into simpler strategies for solving powers of sine x or cosine x. Okay. Next, we're going to look at integrating products of powers of sine or cosine. This is when we have integrals of the form sine to a power of x times cosine to a power of x. And in this case, we're using m and n to represent those powers. If m is an odd positive integer, we split off a factor of sine x, because that means that the power on sine is odd. We're going to pull out a factor of sine and write the remaining even power of sine x in terms of cosine function. This step, when we do it, prepares for the integrand for the substitution u equals cosine x, and then du has that extra factor would equal sine x, which will take care of that extra factor that we pulled off. And the resulting integrand is readily evaluated. A similar strategy is used when n is odd. So if, for example, if the power on cosine was odd, then we would pull out one factor of cosine and then substitute in u equals sine x and do the same thing. Okay. If both m and n are even positive integers, the half angle formulas are used to transform the integrand into a polynomial in cosine of 2x, each of whose terms can be integrated as shown in example 2. All right, so let's look at first at example A, sine of 4x times cosine squared of x dx. Okay, that's the second case that we have down here where they're both even positive integers. So we're going to use the half angle formulas that we just looked at before. So as we know, sine is minus, so we get the half angle formula for sine to the fourth is sine squared squared. So sine squared equals 1 minus cosine x over 2, cosine 2x, excuse me, over 2 squared. The half angle formula for cosine squared x is 1 plus cosine 2x over 2. And so we have this new integral by using our half angle formulas and substituting in. So first, if we FOILed this out and then multiplied it by 1 plus cosine 2x over 2, we would get this integral here, which would 1/8 times 1 minus cosine 2x minus cosine squared 2x plus cosine cubed of 2x dx. All that is the algebra of first FOILing out the first sine squared, and then multiplying that times this other factor of 1/2 plus cosine 2x. You really want to rewrite both of these before you FOIL them out as 1/2 minus 1/2 cosine 2x, and then do your FOIL. And then when you're multiplying that times this other binomial, make it 1/2 plus 1/2 cosine 2x, and then multiply through. I'm not going to do that basic algebra here. You need to be able to handle that. Okay? All right. Once we get to this simplified integral, we still have two powers within the integrand. We have cosine squared 2x and we have cosine cubed 2x. Remember, in all of this section, what we're trying to do is get down to where we have no powers so that we can just simply take the integral of cosine or sine or any of the trig functions and go ahead and solve them. So that in the third term, we're going to use the half angle formula again. We've got cosine squared 2x. Well, cosine squared of an angle using the half angle formula is 1 plus cosine of double that angle over 2. So since we have cosine squared of 2x, the double angle is now going to be 4x. So we're substituting in, using the half angle formula, 1 plus cosine 4x over 2 for this cosine squared 2x. All right. For the last term, we've got cosine cubed 2x, and we're going to do what this first paragraph said. If the exponent is odd, we're going to factor out one of those. So we're going to take out a cosine 2x, and we get cosine squared 2x times cosine 2x. Okay, and then for the cosine squared, we're going to actually use the Pythagorean theorem, where sine squared plus cosine squared equals 1. So cosine squared equals 1 minus sine squared of that same angle. Okay. Here, this is very simple, and all we have to do is, again, make this 1/2 plus 1/2 cosine, actually minus 1/2, because it's minus 1/2 minus 1/2 cosine 4x. And so we can take the integral of all those pieces. Okay. Using substitution, u equals 4x and du equals 4, and then multiplying by that factor 1/4, etc. Okay, so I'm not going to do those simple substitutions to go from here to here. The more complicated substitution, and it's really not complicated at all, if we have this integral here, notice if we make u equals sine 2x, then du is going to be equal to cosine 2x dx. All right. So we can substitute in, and then we get the integral of 1/8 times 1 minus u squared du. And then when we integrate that, we get this final answer down here, which is 1/16x, 1/116 times x minus 1/64 sine of 4x minus 1/48 sine cubed of 2x plus c, the constant of integration. Now I skipped some steps in here, as your book did, because this is basic algebra, foiling and factoring, etc., and then some basic substitution for integrals. Okay. If we look at part B, the problem for part B, where we have the integral of sine cubed of x times cosine negative 2 of x, now we get all nervous, right? But notice this is the same thing. Here we have an odd factor, or an odd power, excuse me. We're going to take one of those powers out and then start simplifying. When at least one power is odd and positive, the following approach works. So if we take out one of these signs, we get sine squared x times sine x times cosine to the negative 2x. Okay? We're then going to rewrite the sine squared in terms of cosine squared, using the Pythagorean identity again. So we get 1 minus cosine squared x times cosine to the negative 2 power of x times sine x dx. All right. If we make u equal cosine x, which is what this is saying over here in this strategy, then we get 1 minus u squared times cosine to the negative 2x would be u to the negative 2. And then the derivative of cosine of x is negative sine of x, so we get du for sine x dx, but we have to add the negative, because we don't have the negative 1 in here, so we have to multiply by negative 1 so we don't change the value. This is kind of like when you don't have a factor of 2, you multiply by the reciprocal, but we don't have a negative 1 in here, so the reciprocal of negative 1 is simply negative 1. Okay. Sometimes students get confused, like, wait, how did we get rid of this u squared and that u2 negative 2 went inside? All we're doing is distribution, right? So if we multiply through, we get u to the negative 2 minus u squared times u to the negative 2. Well, this is u squared over u squared, which is just 1. So we get u to the negative 2 minus 1, but if we apply that negative 1, it just changes the order. U to the negative 2 becomes negative, minus 1 times negative 1 becomes positive, and so it just changes the order. This is a very simple integral to solve, as you can see here. The integral of 1 is u, the integral of 1 over u squared is 1 over u plus c, and then we just simply substitute back in, and 1 over cosine is secant x. So pretty straightforward, etc. And two kind of straightforward strategies to use. And so here are those strategies. When you're doing integrating a product of powers of sine or cosine, if the power on sine is odd, then split off a sine x, rewrite the resulting even power of sine x in terms of cosine x, and then use u equals cosine x. If cosine is odd, then do the similar thing, but split off the cosine, rewrite the resulting in even powers of cosine x in terms of sine x using the Pythagorean, and then use u equals sine x. We saw that example with sine being odd. If they're both even, and we saw this in part A of that last example, we're going to use the half angle formulas to transform the integrand into polynomials in cosine 2x and apply the preceding strategies once again. And again, remember from the last couple of examples, sometimes you might have to do this more than one time to break it down, to get rid of all of the powers on cosine or sine. All right, let's look at another idea called reduction formulas. So imagine we were trying to evaluate an integral such as sine to the power of 8x dx. Well, if we use the method in example 1b, this would take a long time. It's extremely tedious, and we'd have to go through multiple sections where we kept reducing the factor, if you would. Okay, so the reduction formulas have been developed to make these simpler and quicker to solve instead of having to go through all the iterations. What a reduction formula does, it equates an integral involving a power of a function with another integral in which the power is reduced, and hence the name reduction formulas. Okay, you encountered some of these in the last section in problems 50 through 53. And if you want to see how these formulas are derived, you can look at exercises 72 through 74 in our current section 8.3. So once again, sine is minus. So if we are taking the integral of sine to the power of n, this is equivalent to minus or negative sine to the n minus 1, so the exponent is 1 less, x cosine x over the original exponent, plus n minus 1, the original exponent minus 1 over the original exponent, times the integral of sine to the n minus 2. So the exponent of the new integral is actually 2 less x dx. This is a similar formula for cosine, except it's positive. And then we have a formula for tangent to the n of x. which gives us tangent n minus 1 of x over n minus 1 minus tangent to the n minus 2 of x dx, etc. And finally, we have one for secant. Secant to the power of n of x dx equals secant to the n minus 2 x tangent x over n minus 1 plus n minus 2 over n minus 1 times the integral of secant raised to the power of n minus 2. Again, the power is dropping by 2. These are really important formulas for you to know. You need to memorize these. A good strategy for memorizing formulas in my mind, what I typically do is every time I'm doing homework on something like this, I rewrite all of the formulas so that I kill a lot of trees, which is not a good thing, but it helps me to memorize. There's an old pedagogical strategy that says the more senses you use, the greater your recall. So if you just see something, you may recall 20%. If you see it and read it aloud, you may recall 40%. If you see it, read it aloud and write it, you might recall 60%, etc. So every time you're doing your homework, just get out your paper and rewrite all the formulas. After you've done them 2 or 3 times, try writing them without copying them over and see if you memorize them. And then after the second or third time, again, try doing them on your own each time you start your homework, writing down those formulas. So let's try a problem here. Example 3, powers of tangent x. So we're trying to evaluate the tangent raised to the 4th power of x dx. Okay, I've given you the reduction formula there right on the screen. Why don't you hit pause and see if you can simplify this and eventually go ahead and solve this. And I'll give you a clue that you're going to have to use the reduction formula more than one time. Remember, the goal is to get rid of all the powers basically in the integral so that we can solve it using our basic integral formulas. All right. If you haven't hit pause now and go back a little and try it on your own. So remember here now we have tangent to 1 less, so we have tangent cubed over 3, which is the same as 1/3 tangent cubed. N, remember n is our power on the original problem, so n equals 4. So we get 4 minus 1 in the denominator, which is 1/3, times the tangent cubed of x minus, here n is minus 2, so tangent squared x dx. Here, if we use the same formula again, now n is equal to 2, so we get tangent to the 2 minus 1, which is tangent to the 1, or just tangent of x, over 2 minus 1. 2 minus 1 is 1. Tangent of x over 1 is simply tangent of x. Minus the integral of tangent to the n minus 2. Well, since 2 is the n is equal to 2, we get 2 minus 2, or tangent to the 0 power of x dx. Well, anything raised to a 0 power equals 1. Doesn't matter if it's tangent, secant, doesn't matter if it's a polynomial. If anything is raised to a power of 0, this is equal to 1. So this just becomes the integral of 1, which of course is equal to x. And so you can see by using this reduction formula, we made this incredibly easy, and the only integral we actually had to take was the integral of 1. So it's quite straightforward, quite simple. And to show you how much easier it is, let's look at a different kind of approach to this. Okay. We could have also used the trigonometry identity that tangent squared equals secant squared minus 1. This is the Pythagorean identity. Okay, so we could rewrite tangent to the 4th power as tangent squared times tangent squared, and then substitute in the secant squared x minus 1 for one of the tangent squareds. Notice if we multiply through, we then get tangent squared secant squared minus tangent squared. And so we can separate out these two identities. These two integrals. Okay? If we use u equals tangent x, then du equals secant squared x. This is a straight derivative that we know, and that's a simple substitution. Then we get u squared du for the first integral, which is very simple. The integration of u squared gives us u cubed over 3. Okay. And if we again use the identity secant squared x minus 1 for tangent squared, we can rewrite this as the integral of secant squared minus the integral of 1. And well, the integral of secant squared is tangent. The integral of 1 is x. And again, we're subtracting these based upon our original problem and substitution. So we get minus the integral of secant squared minus the integral of 1 is plus that integral, as you can see there. And so notice that we get the same answer in both of these. However, the reduction formula has made, in my mind anyway, this a lot simpler to solve. We now consider integrals of the form the integral of tangent raised to a power times secant raised to a power dx. These are actually evaluated using methods analogous or similar to what we used for the products of sine and cosine. For example, if n, the power on secant, is an even positive integer, we split off a factor of secant squared and write the remaining even power of secant x in terms of tangent x. This step prepares the integral for the substitution of u equals tan x. If m, the power m on tangent, is odd and positive, we split off a factor of secant x tangent x, the derivative of secant x, which prepares the integral for the substitution u equals secant x. If m, the power on tangent, is even, and n, the power on secant, is odd, the integrand is expressed as a polynomial in secant x, each of whose terms is handled by a reduction formula. Example 4 illustrates these techniques. So first let's look at part A of example 4. Evaluate the integral of tangent cubed x times secant to the fourth power of x dx. Okay. We can see that the secant is an even power, so we're going to split off a factor of secant squared and write the remaining power of secant in terms of tangent x. Okay. So here we're going to first split off secant to the fourth power in terms of secant squared. We can see that here. Okay. And using the Pythagorean theorem, as you can see written off to the right, we can then rewrite one of those secant squares as tangent squared x plus 1. Okay? So if we substitute in u equals tangent squared, then we get u cubed times u squared plus 1, and the derivative of tangent is secant squared, and so we get our du equals secant squared x dx, so that takes care of everything there. So if we multiply through, we get the integral of u to the fifth plus u to the first. These are very simple integrals that we can see, and so this becomes quite a simple problem to solve using just trigonometric identities. Here, the only one we used was the Pythagorean theorem, or the Pythagorean identity for tangent and secant, and then some basic algebra. On the last problem that we just did, we could have also used a different strategy because the power on tangent was odd, and so we could have split off a factor of secant x tangent x and then use the substitution u equals secant x. So you could have done this one as well in the last problem. Now let's look at part B, which is the integral of tangent squared x times secant x. And here is where we have the power on tangent is even and the power on secant is odd. And so what we're going to do is to express it in terms of secant x by converting the tangent into secant. All right. So again, we have tangent squared x secant x. Well, remember, an even power of tangent, even if this was tangent to the fourth, we could use the Pythagorean identity, which gives us tangent squared equals secant squared x minus 1. Since there's just a tangent square, we just plug that in. So we get secant squared x minus 1 times secant x. We then have secant x cubed by multiplying through x minus secant x. So we have two different integrals. Okay. If we use the reduction formula number 4, or the last reduction formula, which is for secant, as you can see in the bottom, we get 1/2 secant x tangent x plus 1/2 times the integral of secant x, and then of course this is just brought down. And so we can easily then solve these, the integrals of secant x ends us into this final answer, which is 1/2 secant x tangent x minus 1/2 times the natural log of secant x plus tangent x plus c. Finally, our last slide of section 8.3 is just a reinstatement of those strategies for the products of powers, for integration of the products of powers of tangent or secant. And again, is if the tangent is even and positive, split off secant squared, rewrite the remaining even power of secant in terms of tangent, and then use u equals tangent x. If tangent is odd and positive, split off secant x, tangent x, rewrite the remaining even power of tangent x in terms of secant x, and then use u equals secant x. And finally, if tangent power is even and positive, and secant's power is odd and positive, rewrite the even power of tangent x in terms of secant x to produce a polynomial in terms of secant x, and apply the reduction formula for secant to each term. So these are important kind of strategies, both the products of tangent and secant, or the products of sine and cosine. Okay, so these are things you need to kind of have down in your notes and kind of have in your mindset. You're not allowed any notes for the tests, so make sure that you kind of understand these and are well prepared by the time you get to the next test.